So what does that mean? That means that sigma, the standard deviation, is uncertain in practice. Sometimes it is overestimated, and sometimes excuse me, underestimated. You can see here, with this sample it was underestimated, and this one it was, because we know the true value is 1, yeah? Because it was from a standard Gaussian. So sometimes it's under and sometimes it's overestimated. And in practice you've only got one shot. In practice you've got your data and that's it. You can't just do it again like I've done. And so you say to yourself, right, I'll calculate the standard deviation using this function SD. It's a maximum likelihood estimate, but is it an overestimate or an underestimate? Well, I don't know.
It is.
Hmm?
It just is.
It just is. It is what it is. That's the best you can do. But this plays havoc with the standard error of the mean, sigma over root n, because sigma is unknown. We're now just casually giving you the standard error of the mean, which we covered right at the beginning of the course, yeah? I just casually assume that sigma was known. But if sigma is not known, what's going on is it makes things very difficult. You've got to have a correction for that. And the correction is the t-test. In practice, you use sigma hat as the sorry, it's not variance, it's a standard deviation. But apply a correction. Apply a correction. And I'll show you how that works now. So what we had when sigma is known, this is just revision here. This is just a slight recasting of what we covered in week 1, I think. What you've got is your observations. So x bar equals 1 over n times x1 plus plus xn is your sample mean. Okay, that's just your arithmetic mean of these things, yeah? Mu is the true mean. So if everything was working, the numerator would be 0 because you would estimate the truth, yeah? But of course in practice, the random nature of your observations, xi, your observations are drawn from a random distribution, so it's going to screw you around. Sigma equals standard deviation, and n equals number of observations. Number of observations. Okay, so the difference between the truth and your estimate is, scaled by the standard error of the mean, is standard Gaussian. We covered this weeks and weeks and weeks ago. But the problem is, we do not know. Sigma, we have to estimate it. So we need a distribution for this quantity here. Need to think about x bar minus mu over sigma hat over root n. Okay? And this introduces a correction because we're not using a true value, we are using an estimate of a value. And that estimate may be an overestimate, it may be an underestimate, it could screw you around, it could be wrong, it could be who knows what. It turns out that this is distributed as a t distribution with n minus 1 degrees of freedom. In words, student t distribution which is a correction for the fact that you do not know what the standard deviation is and you have to use an estimate for it. You can tell because I've put a hat over this quantity here. I can't prove that this is the case because to do so would require quite a substantial foray into statistics. But I assert that it is the case and I'll demonstrate it for you numerically. Let's go back to Wikipedia and have a look at the student t distribution. Actually, his name wasn't Student, his name was Gossett, and he worked for a brewery. He worked for the Guinness Brewery. Yeah. And he invented this distribution to account for small sample sizes. We'll see why I talk about small samples in a bit. But he wrote under a pseudonym because he didn't want his employers to know he was wasting his time on theoretical statistics when he should have been drinking beer, or at least making it. So you've got this sort of yin and yang case, known distribution, known standard deviation, and estimated standard deviation. And we can see that nu here is the number of degrees of freedom. If n is large, then sigma hat is almost exactly equal to sigma, i.e. very small error. Okay? If n is large, it should be obvious to you that if you've got lots of data, you're in a position to estimate your sigma very, very accurately. So what that means here is that when nu equals infinity, this corresponds to a very large n. The black line there corresponds to a Gaussian distribution, and we are reduced to this case here. So I'll write that down. I'm running out of space here. If n is large, then sigma hat equals sigma, very small error, and Tn is approximately, in a sense I can't define exactly, approximately n01. So it's approximately normal, and we're back to that case there that we're familiar with. What happens if you've only got a small amount of information? If you've got this light blue curve here, which is nu equals 5, corresponds to 6 observations because it's n minus 1 degrees of freedom. Look what's happened. It's distorted this to account for the fact that we've got an estimate instead of a true value, and it's made the tails thicker, and I'll come back to that later. And as nu equals 2 or even 1, we get this distribution. This is a Cauchy distribution, which has got even heavier tails. What that's telling me is that if n equals small, this thing is dominated, or at least overly dominated, by very, very high values, and your error is likely to be larger because the tails are heavier. Okay. This is a t distribution. We can now apply the same reasoning as before. To calculate a p-value. difference use a t-distribution rather than a Gaussian. Student distribution. Okay. And again, we've covered standard error of the mean before. The only difference, I'm not drawing it particularly well, but this is a distorted Gaussian. It's one of these curves in here that corresponds to your small amount of data. Now, we could go through all the details of all this, but I don't need to do so. I don't need to do so. I can just give you some data. There's a nice example in here. There might be an example in here. I can just cut and paste. Failing that, I'll make some numbers up. Everything's the same as before. We've got one-sided and two-sided tests here. But now it's a little bit more complicated because we need to account for the number of degrees of freedom, which corresponds to the observations minus 1. And if we're on a one-sided, let's take a one-sided 95% test, which has got a size of 5% after all. So we're looking for t-values of 6 and 2 and so forth. But these are on the t-distribution rather than the Gaussian. These numbers here correspond to the t-distribution, not the Gaussian. Oh, it doesn't give an example, so I shall make one up. So there's some numbers. Just imagine these are observations. And again, I want you to think in terms of your portfolios. So you might think these are numbers of the temperatures of my fish tank, or the, I don't know, percentage of questions I got right, or the size of your fish, or whatever it is from your examples, okay? So I'm just making these up as a generic, abstract numbers, but you've got to take those numbers and give them meaning in your portfolios. And I will test the hypothesis. You'll remember we talked about null hypotheses. I will test the null hypothesis. I will test the null hypothesis that the true mean is equal to 0. H0 mu equals 0. Of course, I could change it to be anything. I could say mu equals 10 or 15, as long as I subtract it from my numbers there. Okay. So we'll try to do that. So I'll show you how to do this. What you need here is x minus mu over sigma hat over root n is distributed as a t-distribution with n minus 1 degrees of freedom. That's what I'm going to say. So this thing here is my test statistic, which is this direction here, test statistic. So I'm going to say the probability of having the observation or one more extreme is 5% or below, and I reject my null hypothesis. I'll do a two-sided test. So there's my mean. So you can see we know that the null hypothesis is that the mean is 0. So we've got a discrepancy. So I ask, what's the probability of having that discrepancy or one more extreme, which is more negative than minus 0.46, or on the plus side as well. So we've got a two-sided test here. Okay. So just conceptually, what I've got is this is my test statistic. It looks like that. We've got minus 0.46. So I want there. That's plus 0.46. The probability of seeing the observation or one more extreme, and one more extreme has got this bit and that bit there together. Okay, so we better calculate what this test statistic is. It's minus 3.06. All I've done is calculate this thing here. You can see I've just directly typed it in. And now we need, instead of D norm or P norm, you guys okay? You getting it? You're okay? You ask. If you don't know, you ask. I don't mind. So we've got P norm. You'll remember P norm was the area to the left of the curve. There it is, la la la. What we need now is pt for the t distribution. And just before we do that, we'll just have a look here. You'll see that we've got the same d, p, q, and r, which is random numbers from the t distribution quantiles. This is the one we want, pt. We've got this extra argument, df, degrees of freedom. And ncp is a non-centrality parameter, which I'm not covering because I don't really understand it. And we've got some other arguments too. So to calculate the p-value for our observations, which are here, we need pt, which is the area to the left of the curve. You'll remember, yeah? pt gives me this little area here of, what was it, minus 3.06. It's the same line of reasoning as we had in Pearson's chi-squared test, that we've sucked out one of the degrees of freedom by estimating the standard deviation. It's just the same as in the Pearson's chi-squared test, where we estimated the value of lambda from the data and we subtracted a degree of freedom from it. Is that the p-value? No, it isn't, because we want a two-sided test, and so I've got this area here and I need to double it to get the tail on the other side. There's my p-value, 3.7%. Do we reject the null?
Yeah.
Yeah, less than 5%. Is the null true? Let me show you where the data came from. Remind you. What's the default value for the mean? 0. So the null is true in this case. And hang on a minute, we've rejected it. We have rejected the null hypothesis incorrectly, which is a type 1 error, which should be rare. So unfortunately, events have conspired against me. Well, if look at them, all these are negative. Do you see? How often does that happen? Well, how often does that happen? How often do all 5 end up negative?
96% of the time, according to what you've done.
Oh no! No. This uses the mean value. This uses all the numbers. All I'm interested in here is the sign. It's a binomial distribution. Yeah, because each one's a binomial. It's either positive or negative. It ain't going to be 0. And they're all independent, and I'm interested in the total number of negative signs. So how often do we get all signs negative? That often. Actually quite close, isn't it? So we've got something unusual going on here. Just the general cussedness of nature is conspiring against me. Kind of thing that happens. And we have incorrectly rejected our null hypothesis. If I generate the data again, actually I won't, because what I'll do is I'll show you how to derive that this hypothesis here. I'll show you how to derive that number directly. That's it. R has thought of all this, and you can go t.test of x, and it should come up with 3.7%. Oh. It's always a bit of a gamble, that, because there's so many places it can go wrong. So yes, we can reject the null hypothesis even though it's true, so this constitutes a type 1 error. And you'll have to believe me when I say that's rare. Well, it is rare. It only occurs 5% of the time. And to demonstrate that, if I generate some new x's and test again, here we fail to reject it. And the majority, in fact 19 out of 20 times, you will fail to reject it because the distribution is too small. Because the p-value is too high, I'm sorry. This is extraordinarily useful. Let me just give you some examples of this in use. This is extraordinarily useful, and it gets better too. I'll finish up in a few minutes. So you might consider some kind of a fitness test. And these are times to run a course, before and after some training, after training, I don't know. Yeah, so before it might take you 10.1 minutes, and after it might take you 10.3, 9.8, 9.2, 9.7, 10.1, 10.8, 10.1, and so forth. And you want to know if this training has actually made you run faster. So you look at the difference. Plus 0.2, minus 0.6, plus 0.3, minus 0.7, minus 0.4. So that's the difference. So here we've got the times for this is person A, person B, person C, D, and E. And again, I just want to, I know I'm saying this over and over. Sorry, go ahead.
0.3, isn't it 0.4? 1, 2, third one down.
Oh, yes. Again, I want you to think of how you can apply these techniques in your portfolios. I'm deliberately using kind of stupid data here because I want you to say, his is no good, I'm going to use mine for my portfolio. This could be the weights of your fish before and after. This could be your student scores before and after instruction. This could be your rugby scores before and after a training session. Could be anything from your portfolio. And of course, what's your null hypothesis about the training?
After training, it was.
It's the same, yeah? The training's had no effect. Your null hypothesis is that your training has no effect. Of course it is. That's always your null.
Can this compare two different people?
We will come to that.
Sorry.
Yeah, we'll come to that. We'll come to that. So in other words, if I call this D for difference, then the mean of D equals 0. Of course. Do you see how I'm turning these two numbers into a single number because I'm only interested in the difference? I can't see them from here. Somebody call them out.
2.1.
No, the difference I want.
Plus 0.2.
Yeah.
Minus 0.6. Plus 0.4. Minus 0.7. Minus 0.4.
So yes, oh here we are. Yes, the times have come down by 0.22 of a minute. So you say, right, on the null hypothesis, it's 0. The difference is 0 before and after, for the mean at least. And it's come down, so the training's effective. And then you say, well, hang on a minute, that could have occurred by chance. Is this significant or not? So we go through this process here of calculating this thing here, comparing it to the t-test and looking at the tail area. Do we need a one-sided or a two-sided test?
One-sided.
One-sided. Nobody goes training because it makes you slower. I suppose it might make you more tired. One-sided test. All right? That's actually, so we don't reject it. But that's actually a two-sided test because it does a two-sided test by default. And I can never remember how this works. We'll come to the two, I'll stop for a break in a minute, but we'll come to the two, which is to answer your question after the break. But you can see here we can specify that the alternative, and it picks up the first one of two-sided. So it does a two-sided. We want to test for it being less than 0 or greater than 0. We want to test for it being less than 0. And you can see it's taken the p-value which was there for the two-sided one, but because you've got the two tails, it's giving half of that because it's only a one-tailed test because I'm specifying I'm looking for less than 0. Do we reject it? No, we don't. We don't reject the null hypothesis because the p-value is 18%, which exceeds the 5% cutoff. Okay? So there it is. Now we're in a position to say whether your fish are heavier before or after, whether your students are cleverer before and after, whether your coffee is nicer before or after some process. Yeah? So you can compare Starbucks to other people's coffee objectively. Was it you doing the coffee? Was that you? So don't listen to my examples because my examples suck because they make sense for me. You have to transplant these numbers and these techniques and these concepts into your own portfolios and say, yes, I can use that to assess my problems. Right, I'll stop there for a few minutes and we'll convene at 10 o'clock.